let's look at the question number 6. Is from the 2012 practice exam, a series question. Question 1, use the ratio test to determine the interval of convergence. No hidden question there. Do remember that your ratio test, you must set up a limit as n goes to infinity of the n plus first term over the nth term. There's your general setup. You don't need to write that general formula. What I'll usually do is I'll jump straight to the n plus first term. I'm going to stick that -1 to the n in the numerator with x to the 2n minus 1. So my n plus first term is -1 to the n plus 1. And if I plug n plus 1 in for n right there, that'll be 2 times n plus 1, which ends up being x to the 2n plus 3. All over, same thing, 2 times the quantity, n plus 1 is 2n plus 2, plus the other 3 that's over there is going to be 2n plus 5. And I will multiply by the reciprocal of my original, 2n plus 3 over -1 to the n times x to the 2n plus 1. And now we are going to clean this up. The -1s to the n will cancel all but that one right there. However, the absolute value is going to eventually get rid of that -1 anyway. Do remember to include the -1 to the n in your original ratio. Some of y'all, when you took the quiz, did not do that. I was nice. I did not penalize you for that, but that probably would be held against you on the AP exam. As for the x terms, I have 2n plus 3 on top, 2n plus 1 on bottom. There are 2 more on top. So when those cancel out, I'm left with an x squared in the numerator. And when you think about the absolute value of this guy, as you clean this up, -1 is going to go away. So the absolute value of that is +1. X squared cannot possibly be negative, so we don't need to worry about the absolute values there. And we are left with x squared times 2n plus 3 over 2n plus 5. Some of you are trying to cancel 2n plus 3 and 2n plus 5. You cannot cancel or divide any of that away. As for the limit, top and bottom degrees are equal. Technically, if you wanted to divide the coefficients, it would be 2x squared over 2. However, that is just x squared. And so we evaluate the limit. And then after evaluating the limit, we need to remember that for the interval of convergence, we need the answer to the limit x squared to be less than 1. And I'm just going to think about this logically. If a number squared is less than 1, then I need that number to be between -1 and +1. So we go through all of that. We get our, they call that the interior interval of convergence. But you have to remember that the ratio test, if your limit is equal to 1, is inconclusive. It does not tell you whether the series converges or diverges. So we have to manually test each of those endpoints on our own. So now I'm going to come over here and I'm going to test my original series if x is -1. So if x is -1, I will have the series. N goes from 0 to infinity. And that would be, well, I have -1 to the n already. -1 to the 2n plus 1 is -1 to the 2n times -1. So I broke that up instead of -1 to the 2n plus 1. I separated it into -1 to the 2n and -1. All that over 2n plus 3. And this piece right here, -1 to the 2n, is always going to be positive because you're essentially squaring it. That's like -1 squared to the n. That's always going to be positive. And then you look at the rest of this, it's -1 to the n times -1. That ends up giving me the series of -1 to the n plus 1 over 2n plus 3. And what we have there is an alternating series. So that is an alternating series with my non-alternating part. I'm going to call it a sub n, being 1 over 2n plus 3. And for an alternating series to converge, you need to show that those terms approach 0 and decrease, and that's going to be pretty easy to do. The limit as n goes to infinity of 1 over 2n plus 3 is indeed 0, and the terms decrease. A sub n plus 1 is less than a sub n, because if you plug in n plus 1, we have 1 over 2 times n plus 1 plus 3, and that will indeed be less than 1 over 2n plus 3. And so my function decreases, my series decreases, therefore my series converges. That says converges when x equals -1 by the alternating series test. Then we have to test the other endpoint. So now I also need to test 1. So I think I'll come down here and I'm going to test x equals 1. And my work is not beautifully laid out here. But when I plug in 1, that's going to be a lot easier, because when I plug in 1 for n, 1 to the 2n plus 1 is just 1. So we're left with negative 1 to the n times 1 over 2n plus 3. And we essentially have the same alternating series that we had when x was negative 1. It's just negative 1 to the n instead of negative 1 to the n plus 1. And so this will also converge by the alternating series test. And we don't need to flesh that out in great detail, because we're going to use the same tests that we had right up here for the other series. So it converges by the alternating series test. Therefore, we finally have our interval of convergence. We ended up converging at both of the endpoints. So the interval of convergence is negative 1 to 1. And we will include those negative 1s. And that is a heck of a lot of work for just the first part of this question. And they rewarded you nicely for that. So let's look at the point breakdown on this one. I'm going to uncover my point breakdown. And this is a 5-point question. 5 of the 9 points is right here in part A. 1 point for simply setting up the ratio correctly. That includes the negative 1. If you don't include the negative 1, then you haven't determined the convergence of the original series. You determined the convergence of the series without the negative 1. They didn't ask you for that series that I've just shown you with the negative 1 covered up. They want you to show that the series with the negative 1 to the n also converges, so it needs to be part of your ratio. I was just nice to you and I didn't take off if you did that, but a lot of you are leaving out that negative 1. It is part of the series. Put it in there. So 1 point for setting up the ratio, 1 point for computing the limit. I'll be getting to this x squared right here. 1 point for identifying the interior interval. So if you got to this spot, this is 1 point. So let me see, so we have 1 point here, 1 point here, 1 point for the interior interval convergence. Thanks, Courtney. And then you get 1 point for considering both endpoints. So just considering the endpoints here and here, that's 1 point. And then finally getting the correct analysis and getting the interval of convergence is your 5th point. Thank you. Have a good weekend. So there's all part A, and that's going to be the chunk of this problem. The other 2 parts are not nearly as bad. So let's look at part B. We are using this Maclaurin series for G. We evaluate it at 1/2. They tell us right here it's an alternating series whose terms decrease in absolute value to 0. They're basically confirming that this series can be shown to converge by the alternating series test. We kind of know that already from part A, but they tell us anyway. We use the approximation of 1/2 to using the first 2 non-zero terms of this series, and they give you the approximation, show that the approximation differs from the true value by less than 1 over 200. This is an error approximation method. And for an alternating series, this is an alternating series, the magnitude of your error, the largest your error could possibly be, is that first omitted term. So if we use the first 2 non-zero terms, my first omitted term is going to be the 3rd term. And that's going to be the 3rd term when x is equal to 1/2. So I find my 3rd term, 1, 2, 3. There's my 3rd term. If I plug in 1/2 for x, you get 1/2 to the 5th all over 7. If you wanted to clean that up, that's 1 over 2 to the 5th times 7. 2 to the 5th is 32 times 7. And if you multiply that out, you get 224. And that would indeed be less than 1 over 200. And we're done. And that's all we have to do on that one. Find that first omitted term, show that it is less than 1 over 200. And this is a 2-point question. 1 point for using the 3rd term, and 1 point for declaring that that 3rd term is less than 1 over 200. And then that gets to part C, and this is a quick one. I think the easiest part was part C. We have the first 3 terms here. And we also have the general term. So if I wanted to, I could add this general term, negative 1 to the n times x to the 2n plus 1 over 2n plus 3. And it says, write the first 3 non-zero terms for G prime. G prime, just if this is G, then G prime, you just differentiate that function. This is a nice one. G prime of x is going to be the derivative of x over 3, that's 1/3. Derivative of x cubed over 5, that's 3x squared over 5, plus derivative of x to the 5th is 5x to the 4th, and that's over 7. And then for my general term, The only x term here is that. Everything else is a constant. We're differentiating with respect to x. So the -1 to the n will stay there. The 2n plus 3 is going to stay down here. And when you differentiate x to a number power, you bring that exponent down, 2n plus 1, x, and then you subtract 1 from the previous exponent. 2n plus 1 minus 1 would be 2n. There is your general term, and we are done. One of the common mistakes I saw here is several people differentiated correctly but did not put this in parentheses. If that is not in parentheses and all you did is put like little multiplication dots, then you're only multiplying the 1 times the x. You're only multiplying the -1 to the n times the 2. That plus sign is breaking it up now, so you must make sure you group that whole thing so that we're multiplying all of 2n plus 1 times x to the 2n. And that is the end of this question. This was only a 2-point question. You got 1 point for getting the first 3 terms correct, and then 1 point for the general term. And so this is one where like 75% of your work is wrapped up in part A. And there is an explanation for the 2012. Well, y'all didn't know it's from 2012, but it's the series FRQ quiz we had from a while ago.